honored to be here. Actually, just to give you a reason why I've come here, I'm the executive sponsor for CMU from Microsoft, so I kind of the high-level touch point on the engagement with CMU. And in that capacity, I go to CMU twice a year. I meet with the school heads, I meet with the department heads, I meet with the research faculty and students. I do lectures there as well. But I wanted to go out and University Relations said, hey, do you want to go visit some other schools? And so I got the chance to put together the list of schools that I'd love to go visit. And I have to admit that MIT was #1 on the list because they rejected me as an undergraduate. So, but then Berkeley is on the list as another great school that I've never been to. So looked forward to the opportunity, and it's been a great day here. So the presentation I've got for you this afternoon is one where I thought there's probably a diverse set of background on what cloud computing looks like and what Azure is. So this talk is focused really on Microsoft Azure's engagement with Microsoft Research. Given that there's a lot of research going on here, I thought it'd be interesting for you to see the way that we internally engage with our own research organization on delivering cloud innovations. And in that, to get to that, I put it in a framework of here's an overview, very, very high level of cloud architecture. And for those of you that are interested in what's underneath the hood of a platform like Azure. So I'll go ahead and get started. This is the agenda. So I'll talk a little bit about our data centers, then talk about our networking infrastructure, our server technology, the compute platform, this is logical compute, and then finally wrap up with storage. And starting with our data centers, I thought I'd share with you just the scale that Azure's gotten to at this point. We're in 54 regions around the world. We like to brag we're on every continent except for Antarctica, and that's just inevitably going to come at some point. So this is an expansion that's, we've been essentially doubling every year to 18 months in size. We're up in the scale of millions of servers at this point, and we don't see any end to that growth ending anytime soon. The enterprise is in this tipping point. We estimate, or I estimate, that there's probably 10% of enterprise workload that's in the cloud at this point. But enterprises are going all in on cloud, and it varies across different enterprises who you talk to, whether it's 2 years, I'm going to be 100% in the cloud, 5 years, 7 years, 10 years, but there's no getting around the fact that the enterprise is rushing towards cloud at this point, so that's going to be driving growth for the foreseeable future. Now, the way that we design our logical architecture for data centers is we define what are called geographies. Geographies are countries more and more. They used to be regions like Europe, but now within Europe, we've gone in and defined geographies as UK, Switzerland, Norway, and France, and basically you can imagine that every country is going to become a geo at some point that has any kind of sizable market for cloud computing. The reason that we do that is because customers, not only for latency reasons, but for data sovereignty reasons. So there's businesses in these countries, and the world is becoming much more sensitive about where their data is placed. Companies that are regulated need data within the country borders. The government needs data within country borders. There's private businesses that just have that bias towards keeping data within country borders and under what they feel is the country laws that can protect their data. Within a region, we define within a geo, we define what are called regions. Regions are collections of Azure data centers that are within some proximity of each other. The latency diameter here is 2 milliseconds round trip is what our guarantee is. It's really much lower than that, but that's our promise to customers. And we go into a geo with 2 regions. We pair them together, and we do that so with hundreds of miles typically separating them, and that is so customers can create a disaster recovery solution on top of our platform. We try to keep these regions as independent as possible, so we'll put them on different major floodplains, different tectonic plates, different parts of the grid, and we also try to prevent correlated software failures. So when we do a rollout of software across our cloud, we'll do one half of the region pairs and then go to the other half so that if something happens, customers can fail away from the problem. Now within a region, we've been adopting something called availability zones. This is something that you see with the other cloud providers as well. And this is just data centers within that 2 millisecond envelope that also have uncorrelated failure modes. So they'll be on different electricity, different water, different networking, and also try to avoid correlation in local natural disasters like a local flood. And the reason that we do this is so that customers can replicate data synchronously and get high availability across these different availability zones. It's much more common to have a data center failure than it is to have a whole region fail. And so they can tolerate that without any data loss, which they might experience doing a disaster recovery to another region, because they can synchronously replicate the data between those zones. And that means that if a zone fails or data center fails, they can fail over the workload to the other zone with no loss of data and minimal disruption. Now, when it comes to the size of these data centers, I mentioned that we've got millions of servers. I thought I'd show you some pictures of what these data centers are looking like. This is Quincy, Washington, which is a site of a large hub for an Azure region. The reason that we built it there, of course, is that it's next to the Columbia River, which is a great source of renewable energy. And so what you're looking at here are 8 colo facilities. Those are 8 megawatts of capacity each. So there's a total of 64 megawatts. This is just part of what's in Quincy. There's other large build-outs, but just to give you an idea of the size of these things. This is Cheyenne, Wyoming, another place where there's great sources of renewable energy. And those colo facilities down there, you can see those are 8 megawatts a piece. There's the same data center design as we saw on the previous slide, but you can see a bunch more land being cleared for more data centers. Then you can see Dublin. Dublin, there's actually 6 data centers in this picture. The interesting thing about this picture is you can see they all look different, and they've evolved over time. So we used to have the HVAC systems next to the building. Now they're on top of the building. So you can see that kind of evolution there in this picture. And we're continuously evolving our data centers. We're up to our 7th or so generation of data center design. Each one brings down brings up efficiency, so reduces waste of electricity, what's called PUE in data center terms. And we're not done innovating there. Here's Amsterdam. Another 32 megawatts there, another cleared land for more data centers there, and then you can see renewable energy sources that we've got in Amsterdam. Now, we're always trying to improve the efficiency of our data centers and minimize the environmental impact of them. One of the projects we've got with Microsoft Research is something called Project Natick. Now, the thesis they had is that we can drop servers into sealed containers on the ocean floor, and we get a few benefits potentially from them. One of them is that we can use potentially currents for power. We also can use ocean water for cooling. And there's some other benefits I'll talk about in a second, but I thought I'd show you some pictures. Now, this is the experiment V2 of Natick. The first one was just one rack that we dropped about 30 feet off a pier in about 30 feet of water. This cylinder was created in France, and you can see that there's 12 racks here. There's roughly 800 servers in this cylinder that are going to be sealed. The air is going to be evacuated from the cylinder. It's water cooled, and also all the particulate matter is also sucked out in that process as well. We went from manufacturing this cylinder to having it powered on the ocean floor in 30 days. And so this is another goal of ours, is to be able to provision capacity as it's demanded, rather than today's lead time for data centers, roughly 18 months. So you've got to start building out way ahead of when you see the demand coming. We dropped this one into about 100 feet of water, a kilometer off the coast of Scotland in the Orkney Islands. And we're working with the European Marine Energy Center, which is focused on renewable energy sources. On that, you can see that the temperature in the water at that depth is very low, so you can see it's about 12 degrees Celsius. This keeps the data center, the servers inside the data center, very cool naturally. And there's very little emission of heat into the water that can be easily dissipated in that kind of volume. We're going to deploy this for 5 years, we think, and watch this. We've got control experiments on land with the same servers in land conditions, in a variety of different conditions, so we can see how these compare to one another. The goal here, or the benefit that we also think we can get from this, is by having it at a constant temperature, unlike land-based data centers that have fluctuations in temperature, with no humans touching it. Again, on land data centers, we have people touching the servers to repair them. This will be fail in place. That both of those, plus no particulate matter, no water vapor, these servers will last longer. And so that's what this experiment's aimed at. Here's a picture of it being loaded onto the gantry to be towed out to being dropped. Here it is there being dropped into the water. And then here's the electric and network cables being dropped to be connected to that cylinder. We're also looking at impact on the environment. And you can see a bunch of the things here: people, oysters, dust and gas contamination, thermal cycles. So these are the benefits that I've already mentioned to you. But nevertheless, our AI for Earth group in Microsoft Research is interested in, is there an impact to the environment that we're not aware of, positive or negative? So let's go look at that. And so you can see that we've got cameras hanging off this thing that are looking at the flora and fauna around it, and they're tracking the health of that ecosystem around there to see if there's any effects. So that's a look at data centers. Now let me talk a little bit about our network architecture. So this slide shows you comprehensively all our network services, from our global WAN there you can see is the cloud there. This is what connects all of our regions together. It connects to peering points with other network providers. That on the left side are our Azure regions. You can see that there's something called regional network gateways that connect the local data center networks to our global WAN. And on the far right, that's where customers are. That's where ISPs are. That's where enterprise networks are that connect into our dark fiber backbone. Then as far as services, we've got services like front door service that does SSL termination and caching on the edge. We've got services that allow for firewalls to be implemented in the cloud for on-premises services. We've got virtual networks in the cloud that allow you to isolate virtual machines and even cloud services from one another and from the internet. So all of these, you can see a full list of services that continue to grow in the networking space. Now, Azure's built on top of this dark fiber backbone, which is the second largest dark fiber backbone in the world. This is all owned and leased by us. In fact, we've made huge investments in building this out, including dropping new subsea cables. You can see that dotted line there goes from Spain to Virginia. That is the Maria subsea cable, which we launched about 2 years ago. It's 160 terabits of connectivity between Europe and the US, the largest of any subsea cable. That was a joint project, by the way, with Facebook and Telsus. And the reason we dropped it there is the other cables crossing the Atlantic go from England to New York. And so there's kind of a fragility there. And so this creates a secondary route that can survive in the case something happens to the other one. What you were looking at on that slide is over 100,000 miles of cable in our wide area network. Now, logically, though, our network is built on something called software-defined networking. So this is a buzzword that showed up in the last 5 to 10 years. Companies made billions of dollars being sold because they had SDN technologies, like to VMware, which I see a VMware shirt right there. And SDN is best understood when you look at what IT networking looked like, which is proprietary appliances with management, control, and data planes all in one box. And Azure actually launched initially with load balancers that were these proprietary appliances. We found out very quickly they were very expensive, they were fragile, they didn't scale, and so we worked on defining software-defined networking. This is where we take each of those layers, we pull them out, and we implement them in software as cloud services effectively. That lets us get the availability and scalability that a cloud service can get just by, you need some more capacity, just allocate some more servers or virtual machines underneath. You need high availability, well, we've got redundancy built into the software control plane, so if servers fail, customers aren't impacted. Now on Azure, if you take a look at the overall network architecture, this is the overall network architecture of the Azure platform. And what we've got at the bottom is the infrastructure, the servers I was just talking about. The layer above it is a hardware manager that's responsible for provisioning, managing the lifecycle of servers, taking them out of rotation if there's problems. The Azure Fabric Controller manages virtual machine deployments. I'll come back and talk about that a little bit later. And then we've got services built on top, compute network storage, and then higher level services like PaaS services that are built on top of that. You can see that we also have role-based access control and telemetry systems and identity that are cross-cutting across the platform. At the very top, you see Azure Resource Manager. That is our universal control plane for Azure. So resources plug into that and expose their services using a common schema and common API, and that means that all services, when they plug in, get role-based access control and policy and monitoring for free, just as being part of the Azure control plane. And above that, the portal, command line interface, and PowerShell are the ways that, and REST APIs are the ways that customers interact with the platform. Now we pull out networking by itself, and we've got the resource manager at the top, and we've got a network resource provider that plugs into Azure Resource Manager, and a compute resource provider, because network doesn't mean anything without the compute that uses the network. So there's a dance that these two systems orchestrate to land a virtual machine on a server and get the network wired up to it. It's the compute resource provider is responsible for talking to its compute controller that talks to its own representative on the server to launch a VM, and then network has its own agents on the VM that talk to controllers, some of them regional controllers in scope, that wire up virtual networks and network security group rules and load balancers to that virtual machine. All software defined. Now, one of the challenges we have in building out our network, the way we're building it out, is that we're adding new data centers all the time. Every few days, we launch a new data center at this point. And whenever we launch a new data center, that's bringing a bunch of new network hardware onto the network and establishing new routes. And so one of the problems that showed up is manually setting up those routes is you can make a mistake. People can make mistakes, and black hole traffic. And you can actually black hole traffic for the world if you make the wrong mistake. Certainly for Azure's network, we could make a mistake and bring down, basically cause a region or multiple regions to go offline effectively. So there's no way for us to make sure that humans don't make mistakes. So what we've done is put in automated systems to verify that when we do make changes to the network routing rules, that they're safe. So this project with Microsoft Research, Azure Network Emulator, actually emulates our network devices with high fidelity, including their bugs and non-documented behaviors, so that when we take our network configuration, we can give it to the system and then simulate what would happen, and then verify that all the routes are valid and that we're not blocking only traffic. This is a project now. It's been in deployment in production for about a year. We've done 25 million compute hours, core hours of emulation of network changes on this. And we estimate that we prevented roughly 100 regional black hole type of events using this emulator. So this has really made it, the only way we've gotten to the scale is with something like this. Now, whenever there's references to the research papers that we've published or blog posts, they're at the end of these sections. So I'll make these slides available to you, and you can go and read more if you'd like to. And the CrystalNet paper there has been published in an academic conference, but also there's the research report right there for it. All right, let's take a look at servers. Now, I thought this would be interesting for people that haven't paid attention to what's going on with cloud, or remember cloud as the old commodity servers that just scale out days of roughly a decade ago. It's changed a lot since then. So I thought I'd take you on a trip down memory lane just to show you how much server technology and cloud use of servers has changed in that time. This first server, Gen 2 we call it, was the first server that we deployed in Azure. So when I joined in 2010, this is what we had a few thousand of in Azure. And they're 12 core servers with 32 gigabytes of RAM. They have 1 gigabit Ethernet attached to them. Now I'm going to fast forward here. There's our Gen 3. And you can see the scale here vertically in terms of number of cores. The width is RAM. Here's our Gen 4 from about 4 or 5 years ago. Then we introduced something called Godzilla. You can see a big jump in RAM and cores. The reason we introduced this, we have enterprises that are moving high demanding database workloads, specifically SAP, into the cloud. It's one of the first workloads that a lot of enterprises move. And those are extremely RAM hungry and CPU hungry. This Godzilla SKU has 512 gigabytes of RAM and has a 40 gigabit NIC on it. So we'd switched to 40 gigabit networking a few years ago. Then our standard machines, here picking back up, Gen 5. This has 40 cores on it and 256 gigabytes of RAM. Here's our Gen 6, which is what we've been deploying now. This has 768 gigabytes of RAM. Interesting thing here is just less than 3 years after Godzilla, our mainstream server that we're deploying at scale has more RAM than what we considered our extreme shock and awe SKU of that time. And then we just introduced this. This is, we call it the Beast. This one has 4 terabytes of RAM on it. And we've just announced 12 terabyte RAM servers as well. So there's the 12 terabyte RAM server. And this, again, driven by SAP HANA workloads. We also go in the other direction. We also go into edge hardware, too. And one of the pieces of edge hardware we introduced is something called Azure Sphere. It's called an MCU. It's got about 4 megabytes of RAM. So in terms of beasts, it's 0.00000000533 equivalents of a beast, B2. And this is aimed at, of course, IoT devices and secure IoT devices that connect up into Azure. So another type of hardware that we've been investing in are FPGAs. The way that we've accelerated our network is by offloading the SDN processing, the data plane processing, onto FPGAs, rather than have that happen on the CPU cores. But we're using FPGAs in other ways as well. One of the ways is through through inference for machine learning. And so if you take a look at what an FPGA is, it's a programmable piece of hardware. It comes with logic elements and RAM and DSPs and bus connectors and USB and controllers. The FPGAs can be flashed with updates to the software and basically create a new circuit. So if you take a look at from efficiency, cost and performance, or power and performance, there's 2 ends of the scale. There's dedicated devices that are hardwired circuits. You can get great performance and very low energy on that end. And then the other end, you get CPUs, which are very general purpose, not very power efficient. And then in the middle, you have GPUs, and then FPGAs, which are more towards the ASIC side. So the FPGA side lets us experiment with new circuits, and then we can later harden those circuits, what we call is putting them into ASICs. And so one of the ways that we're leveraging this flexibility is with machine learning, because machine learning models and algorithms and techniques are constantly evolving at a quick pace. So rather than, for inference, burn these things into ASICs, we're letting the FPGAs be programmable. And what we can do is take a deep neural network and program it right into the FPGA. We launched this as a service about a year ago, and we've been making this more flexible. So there's roughly somewhere around 10 different models, DNN models for image, largely, and speech that we've mapped onto the FPGAs. We're letting customers customize the weights, and eventually we'll let them bring their own models and put them on the FPGAs. And this, customers don't have to know anything about FPGAs. They simply provide us their models using the Onyx model intermediate representation, and then we'll take and put them on the FPGAs. I want to show you a quick demo. This is work that's come out of MSR, and MSR has also been using it for other projects. So we've got a project called AI for Earth, which is looking at leveraging technologies for good, social good. One of the projects here is mapping the United States. This is a project done with Esri, mapping company, and the Chesapeake Conservatory. Just to give you an idea of how this is transforming things, in the past, satellite images have been taken of the US, 1 square mile images, and then looked at by humans to classify the land, whether it's water or forest or industrial, or you get the idea. And this process would take roughly 6 months, a team of people to go and analyze all these images. So working with this, we've automated the process, and I'm just going to show you a quick look at how we would explore. Oops, I don't know what happened there. Hopefully the network's going to be friendly here. I don't know. Yeah. Well, it's actually the network. I'm not. Yeah. Blame it on the network. So hopefully this will come back here in a second. This is a virtual machine running in Azure. And I'm accessing it over the local Wi-Fi network, but it seems that the image is frozen, which means I'm not getting any connectivity to it, which is a little disappointing because I've got 2 demos, including this one, that I wanted to show you. Okay, well, I guess one of the things I can try is, so it seems to be a delayed reaction too. What's that? Yeah. Yeah, that's what I'm on. All right, well, I'll come back later and we'll see if we can do that demo again, but rather than spend our time on that, trying to get that to work, let me go back to the presentation. What I would show you is that using Brainwave and the FPGA image classification algorithm, we can classify those images one by one. So this is what we call real-time AI. Compared to a GPU, roughly an order of magnitude more throughput with lower latency on the classification of those images. And so that's an example of us, what we call using, defining real-time AI for inference using FPGAs. Okay, now the clicker's not working, so I'm in demo hell at this point. Actually, my whole laptop, oh, there we go. Okay, we're back. So let me talk a little bit about compute now. This is the same architecture diagram, but the compute services obviously compute there, that box, that's virtual machines. That's responsible for launching virtual machines using that fabric controller I mentioned before. Then above that, though, we have container orchestrators. Kubernetes is the dominant container orchestrator in the open source world, and so we've got our own managed Kubernetes service called AKS. The world is moving towards containers. It's still not there, so just the leading edge of ISVs and some enterprises are on containers right now, adopting Kubernetes. The vast majority is still back on virtual machines. But the way the world is going is not just containers on top of orchestrators, but serverless models, where the customer packages their code as a container, but then just gives it to the cloud platform, and we run it for them and scale it for them, and they pay for only the resources that that container uses as it uses it. We take a big step in that direction with something called Virtual Node. Virtual Node is a project, open source project we worked on with AWS that allows you to back or to create a node that you attach to the Kubernetes cluster that can be backed by whatever. So it just talks the node protocol, which a node means server. And so you could have, what we've done is we've got a serverless container infrastructure, meaning that you can go launch a Docker container on Azure without ever creating a virtual machine. We'll launch that container inside of a virtual machine someplace for you. But we've created a virtual node connector for AKS and ACI that lets you say to Azure Kubernetes Service, here, there's a virtual node now as part of the cluster, and when I deploy my containers, put it on the virtual node. So at that point, you've got a serverless Kubernetes. You don't have to deploy any virtual machines. The control plane is managed by us and hidden from you. And now the data plane where the pods or containers run is also now serverless. You never have to worry about spinning up VMs, managing them. Just deploy your containers, scale them up instantly, scale them back down. And we've also, to try to help customers get to serverless, one of the challenges has been to this point is that serverless business models have priced them such that if you run them a serverless container for over a few hours, it becomes more expensive than if you just launched a virtual machine and ran it for that long. So we've dropped the price of Azure container instances to match virtual machine pricing. So now there's no pricing reason to not go serverless. Now, one of the research projects we got with MSR in this space is something called Resource Central. And this is an umbrella project name that just uses data that we produce about virtual machine usage in our cloud to solve a bunch of problems. And these problems that we've identified that we can solve with this are implementing more efficient schedulers for virtual machines. Based off of historical usage by customer of virtual machines, we can predict with pretty high accuracy what they're going to be doing. And if we got that prediction, then we can make sure our allocations most efficiently match that. We also can do efficient server maintenance. We can do power maintenance too, so we can spread power by knowing what the virtual machines or how they're going to behave ahead of time. We can even the power usage across our data centers. So a bunch of different benefits we get out of this. Just to give you an idea of the resource utilization issue, here's what we're trying to do is maximize the use of resources. It's a multi-dimensional problem. There's RAM, there's network, there's CPU. So there's a number of different dimensions, and what we try to do is maximize overall the availability of those resources when we do a new placement, so we don't run out of one before the rest. If you take a look at this scenario here, you can see on the left, there's wasted memory there on that server. We've consumed all the cores, but there's still RAM, and so this is an inefficient use of our capacity. On the right side, we've packed a high memory instance there in the few extra cores, and now we've fully maximized all the resources on that server. So here you can take a look at how prediction can help. We've got a virtual machine A. It's a small virtual machine. It's 1/4 of a server. There's 2 servers there, node 1 and node 2. The one on the left has 1 3/4 virtual machine on it, and the one on the right has 3 1/4 virtual machines on it. The question is, which server should we put this new VM on? Well, if we know that VM B is going to be coming along later because of our prediction, this is a full server size virtual machine, we can determine use that in our allocation. And so the math, for those of you that are interested in probability and statistics, and I'm sure there's a lot of people here that know it much more deeply than me, but this will give you the different probabilities. If you say that virtual machine, virtual machine is going to have a 50% probability of terminating after time t, then we can determine, hey, we should put this thing actually on node 1, because we'll have a much higher chance of those 2 virtual machines terminating than the other 4 on the other server. And so that way, when that that virtual machine B comes along, we've got enough space for it. So that's just a simple example. And there's you can see that we're taking a look at a bunch of different characteristics and predicting using different machine learning algorithms. And you can get more information about that here in that research papers from SOSPI on Resource Central. And we've actually made the data set for the traces we used in that paper available to you. So if you're interested in looking at real-world virtual machine deployment behaviors, you can do that. So also in computing, one of the challenges that some of our customers have with putting data in the cloud is sensitivity over the data. I put the data in the cloud, and now a malicious admin can leak my data, or a hacker can break into the multi-tenant infrastructure and grab the data and exfiltrate it. Or a third party, like a government, can come along and subpoena Microsoft and compel us legally to give customer data without their knowledge or consent. We want to be outside of all of these. We want to protect customers against these threats. We don't want to be in between them and law enforcement. We want normal due process of law to take place when possible. So what we've been investing in is something called data protection and use, or data encryption and use. Data encryption at rest, obviously, data encryption on the wire, everybody's familiar with that. What's been missing is keeping the data effectively encrypted while it's being processed in the cloud. And you can see that there's the homomorphic encryption is one way to do that, and we're at Microsoft Research is investing in homomorphic encryption. But another more general purpose way to protect it is using something called software or trusted execution enclaves, or TEEs. These are effectively black boxes, you can see over there on the right, where you can put code and data into it that's now not visible outside that enclave on that server. Even with physical access to that server, you can't see what processing is happening in there, because all of the data, when the data leaves the CPU, it's encrypted and put in RAM. So you can't even put a RAM analyzer and see with the data. So, examples here are Intel SGX, but there's also software-based ones. Depending on your risk level tolerance, we can implement enclaves in software. There's also ARM Trust Zone is another example of enclave technology. So we're investing heavily in, first of all, making SGX hardware available in our cloud. This is through partnership with Intel. And we're also developing software technologies to make it easy for our own software developers, as well as customers in ISVs, to develop software that takes advantage of this capability. something called the Open Enclave SDK. We're going to be making some more announcements in this space at Build conference in about 3 weeks. So stay tuned for some more announcements on confidential computing there. But I thought I'd share with you one of the really scenarios that is drawing a huge amount of interest from our customers, and that's confidential multi-party machine learning. And I've got hopefully a demo of that. We'll see if this comes back. I wonder if I can just reconnect to this virtual machine. Okay. All right. Looks like this demo is not going to work. I don't know what's going on. Looks like that VM is not in a good state. No, it's not even responding. Okay. Well, I apologize for that. Imagine, if you will. The scenario here that I was going to show you. Oh. Is it really here? It's like Explorer's. It's hung. Yeah. Well, actually, it looks like there's a Windows bug that I've hit here, which I've got a predilection for finding bugs in any piece of software that I touch. And it looks like I've hit one here. So here's the land use mapping app. So if I click on this, North Redmond, you can see that this is the kind of classification it'll do that's programmed in the FPGA. Now let me show you AI for Earth. Actually, what I'm going to do is compare the performance of CPUs with GPUs and FPGAs. Now, caveat here, this is feeding these processors one image at a time. So this is not batching. So here, when we do it on a CPU, you can see about 6 images a second. On a GPU, about 60, so order of magnitude more. On an FPGA, on the Brainwave FPGA, about 500. And what you can do with the Brainwave service is dynamically scale the FPGAs up to 800. So you can see that with this, we can classify the entire United States in 10 minutes, which is something that used to take 6 months. And we can do it for the cost of about $80 on top of those FPGAs. So that is that. Now let me show you the multi-party machine learning. So scenarios here, I've got 2 hospitals. They've got their own data sets. They want to do machine learning training on the combined data sets, but there are regulatory reasons they're not allowed to share the data with each other. But with confidential computing, they can establish trust in an algorithm that they both run in an enclave. So here I'm dragging. This Windows is just, oh, there we go. Dragging a data set here. Actually, now it's the network. I'm pressing that button, but nothing's happening. So I'll just talk through this, and if it catches up, we can actually look at it. But what I'm going to do is encrypt this with a key that we make available to the enclave. And then the data, as we send it in, is encrypted such that only the enclave, that machine learning algorithm in the enclave, can decrypt the data. Then I switch to Hospital B, and I do the same thing with Hospital B's data set. Now the machine learning algorithm, that enclave, when it has both data sets, does the training and produces an encrypted model that then Hospital A and B get their own copies of. And now they can go take that model and deploy it and do inference with it. And what I was going to show you is that this is a breast cancer, 2 breast cancer data sets. The accuracy with just Hospital B's data is about 80%, and with the combined model, it's a little over 90%. So showing you how combining these data sets. And like I mentioned, health is one of the sectors we're seeing a tremendous amount of interest in this. But you can imagine lots of other verticals in the enterprise are interested in sharing data sets. And so this is caught up. I've already talked through it, so I won't waste time wrestling with the network and wasting some more time here. But we strongly believe that confidential computing, while it's really for just very kind of limited scenarios right now, given the maturity of enclave technology, the maturity of the tools for building confidential apps, is pretty limited. But over the next 5 years, it's going to mature pretty quickly, and you're going to see that this will become eventually the way that all data is protected, not just very sensitive data, but this will be effectively creating walls around data to keep even moderately sensitive data away from people that shouldn't have access to it. Back to this. We've been doing tons of work with MSR on this, MSR Cambridge. And so not just how we get algorithms and ML algorithms into an enclave and working efficiently, but also with compiler tools to prevent side channel leaks of the code. So oblivious RAM computation. So you can see a bunch of work in this area. Actually, there was a Berkeley link there, too. PLDI paper. All right, so final section. Let's talk about Azure Storage. This is the architecture of our Azure base storage server. So we've got something called Azure Data Lake, which is when enterprises are going and putting data into the cloud, they're now creating what are called data lakes, you might be familiar with, which is let's put all our data in one place and then we can compute on it from a bunch of different directions. And our data lake technology is implemented like this. We've got a distributed file system layer that actually puts the data on servers and replicates it 3 times across different servers and different availability zones. We've got a partitioning layer that takes partitions and maps them to servers, and we've got front-end servers that are effectively stateless or cache and are sitting behind load balancers. Then we also have geo-replicated storage, so these storage accounts can be replicated across regions. I mentioned the region pairs before. And so that's where the partition layer would orchestrate replication. Now, one of the things that we've constantly doing is re-architecting our cloud platform. And storage is a great example of that. We initially started with storage stamps. So these things were isolated deployment units. Your storage account was completely contained in one of these. Your blobs were completely contained in one of these. And while this is great for just stamping out new instances and scaling up, it's not a great customer experience because you basically are limited to, your account size is limited to the size of that stamp. Your bandwidth to your blobs are limited with the bandwidth to that stamp. So about 4 years ago, we started re-architecting our storage service to blow out the layers and make them each independently scalable. And there's a little more complexity than that, but you get the idea. And now what we can do is have a single storage account or even a single blob consume every byte of storage in a region and every byte of network bandwidth off those storage servers. Idea is to be infinitely scalable. And so right now, you can get basically exabyte size files, blobs, on Azure Storage using this new architecture. And also the bandwidth you can see here, in the previous architecture, a 5 terabyte blob took 12 hours to upload to us. And once if you move to this architecture, which we're moving customers over to, you can upload in 14 minutes or less. So you can opt into this, and we're also migrating customers. But we're also working on bringing down the cost of storage. So I don't have to tell you that, especially this group, that data is the new oil, which is what people say, and you never know when data is going to be useful. So one of the challenges in the past is data storage is expensive, so filter your data, save only what you think you need, and you might be throwing out useful data that you can come back to later to gain new insights out of. Wouldn't it be great if we could just keep everything? And the only way you can keep everything has to be very, very inexpensive, close to zero. And we're actually working on technologies that can bring it down close to zero. One of them is by leveraging glass. So this is a project with MSR, Azure, and the University of Southampton to encode data in glass. The idea is that glass, silicon, is the most common element on the planet, basically infinite supply of it, very cheap, and it lasts forever, and it's extremely durable. And you don't need special devices to read and write to it. All you need is light. So how do we do this? And then you can see Azure logo here with data encoded into this. And I'll talk more about how we do that. But we use laser pulses, femtosecond laser pulses. The challenge here, the research challenge is, how do you etch data into this with high density without compromising the integrity of the glass? If your laser pulses are too slow, you cause deformations, and then it becomes impossible to read the data back out. So you've got to be very precise. We also go multiple layers, and we encode multiple bits in each what are called a voxel. So we started with 3 bits per voxel. We're up to 20 bits per voxel. And we're up to 120 layers now of encoding in glass. So we just hit that milestone a couple weeks ago. And you can see the lasers etching. Here's what the reader looks like. So there, you can see it reading those etchings over there. And then we're actually applying machine learning algorithms on top of those images to read the data back off. So this is doing a Z-scan through the layers. Data layer 14, 15. So we're going to have to wait till it gets to 120. Just kidding, we're not. But you get the idea. And then we take the multiple images and we determine the retardation and orientation. This is just a simple 3-bit voxel example just to give you an idea. By looking at the combination of those, we've encoded data we can read back out. I'm actually going to be showing a video at Build conference of, and this is kind of the one that makes people gasp, is taking a piece of this glass with the data etched in it and dropping it in a boiling pot of water. And of course, it has no effect on it. So this is like very durable storage medium. Lasts literally or probably lasts longer than the Earth is going to be around. Now we're taking a look at other technologies too that can be even cheaper. This is one with the University of Washington Microsoft Research in Azure called Project Palix, and this is using DNA to encode data. So you get 1,000 times denser than tape, lasts 2,000 years if you keep it at the right temperature. Obviously, DNA is free. So the way that we do this, we take the DNA, encode data into it, and then to read it back out, you simply sequence it the way that you do any kind of genomic sequencing to read it back out. We just hit a milestone last week where we, in a fully automated way, encoded the word hello into a piece of DNA and read it back out. So that's the point that this project's gotten to. The promise here is there's 20 terabytes in the tip of that. But at that density, that rack can hold a zettabyte of data. Now, just to put that in context, the total amount of digital data on the planet is estimated to be something like 50 zettabytes, or 70 zettabytes, or 100 zettabytes. And so you can imagine sticking all the data in all the world in just a few racks of DNA. So this, so we're just obviously the bottom line here is that we're working with MSR to really do disruptive things and bring innovations that are going to just dramatically transform things, not just go linearly, but also take some of these quantum leaps. And I didn't mention quantum computing, but we're also got a project that started in Microsoft Research on quantum computing. Now that is actually part of Azure as of a year ago, because we are going to bring quantum computing out to the public in Azure as one of our cloud computing capabilities. Don't ask me when that's going to be, because everybody has a different answer. And you talk to the quantum scientists and they'll say 3 years. You talk to the engineers, they'll say 5 years. You ask me, I'll say 7 years. So you can take your pick, but it's coming. So that brings me to the conclusion. The goal here with Microsoft Research and any kind of research we do in Azure is really, if you take a look at all those projects, they're all aimed at one of these dimensions of improving the platform. Security, cost, resource usage, high performance, which also is aligned with cost, high performance and massive scale. So if you've got projects that you are working on that are in these areas, and including machine learning, we've got projects with MSR on large-scale machine learning training. This is kind of the next big frontier of trying to do massive machine learning training with massive models on the path to artificial general AI, AGI. And so that's a hot space too at Microsoft and Microsoft Research in Azure. So with that, I think I'm right at time, but I don't know if people want to ask any. We have time for questions.